Welcome to the Unit 11 Section 2 video on probability. An experiment is an activity involving chance. Each repetition or observation of an experiment is a trial, and each possible result is an outcome. The sample space of an experiment is the set of all possible outcomes. So, if we have an experiment of rolling a die, the sample space is 1, 2, 3, 4, 5, and 6, because those are the possible outcomes of rolling a die. When it comes to tossing a coin, you can either have heads or tails. Spinning a spinner with 4 numbers, your outcomes are either 1, 2, 3, or 4. We're going to identify the sample space and the outcome shown for each experiment. So for tossing 2 coins, the sample space is heads, 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 tails, tails, heads, or tails, tails. And the outcome shown here is heads, tails. Spinning a game spinner, our sample space is 1, 2, 3, and 4, and the outcome shown here is 2. An event is an outcome or set of outcomes in an experiment. Probability is the measure of how likely an event is to occur. Probabilities are written as fractions or decimals from 0 to 1, or as percents from 0% to 100%. So we have an impossible outcome, which is 0%. Events with a probability of 0% never happen. Equal chances involve a 50% probability. Events with a probability of 50% have the same chance of happening as not. And something that is certain is a 100% chance probability. Events with a probability of 100% always happen. Then you have in between impossible and equal chances, events that are unlikely, and events between equal chances and certain that are events that are likely. So between 0 and 50% odds or probability, we have unlikely. And if your probability is between 50 and 100%, then it's likely to occur. So we're going to write impossible, unlikely, equal chances, likely, or certain to describe each event. There are 31 days in August. Well, every August has 31 days in it, every single time. So that is certain to occur. There's a 100% chance that if you're in the month of August, it will have 31 days in it. Carlos correctly guesses a number between 1 and 1,000. That is unlikely because our probability is 1 in 1,000 chance, which is certainly less than 50%, but it's not 0. So while it's unlikely he's going to correctly guess the number, it's possible that he could. So it's unlikely, but not impossible. A coin lands head up. Well, if a coin has 2 sides to it, and you have a 50-50 shot of it being heads or tails, then you have equal chances. Cecilia rolls a 10 on a standard die. This is impossible because the numbers on a standard die only go from 1 to 6. Therefore, it is impossible to roll a 10 with 1 die. You can estimate the probability of an event by performing an experiment. The experimental probability of an event is the ratio of the number of times the event occurs to the number of trials. The more trials performed, the more accurate the estimate is likely to be. So an experimental probability, you're going to have the number of times the event occurs divided by the number of trials. An experiment consists of spinning a colored spinner. We're going to use the results in the table to find the experimental probability of each event. So the spinner landing on blue. Well, we have it happening 8 times out of 7 plus 8 plus 5 trials. So the number of trials we had here was 20. That's 8 out of 20, which is 2 out of 5. A spinner does not land on green. So for the number of times the event occurs, if it's not green, it's got to be red or blue. So we have 7 plus 8. And then on the bottom, again, 7 plus 8 plus 5, which is the total number of trials. So we get 15 out of 20, which is a 3 out of 4 chance that the spinner does not land on green. You can use experimental probability to make predictions. A prediction is an estimate or guess about something that has not yet happened. A manufacturer inspects 800 light bulbs and finds that 796 of them have no defects. What is the experimental probability that a light bulb chosen at random has no defects? Well, we're going to take the experimental probability that a light bulb has no defects, which is 796 out of 800, and that comes out to 99.5%. The experimental probability that a light bulb has no defects is 99.5%. The manufacturer sent a shipment of 2,400 light bulbs to a retail store. We're going to predict the number of light bulbs in the shipment that are likely to have no defects. So now we have found by experiment that 99.5% are not defective. So we are going to find 99.5% of 2,400 by taking 99.5% expressed as a decimal, which is 0.995, and multiplying it by the total number of light bulbs, which is 2,400. And that gives us 2388. So the manufacturer predicts that 2,388 light bulbs will have no defects. When the outcomes in a sample space of an experiment have the same chance of occurring, the outcomes are said to be equally likely. Equally likely outcomes include something like a spinner, where all 4 parts of the spinner are the same size. So therefore, there is the same chance that the spinner will land on any of the colors. Not equally likely outcomes occur when parts of the spinner are different sizes. There's a greater chance that the spinner will land on blue than any other color. The theoretical probability of an event is the ratio of the number of ways the event can occur to the total number of likely outcomes. So for theoretical probability, you're going to take the number of ways the event can occur and divide it by the total number of equally likely outcomes. An experiment in which all the outcomes are equally likely is said to be fair. So, for example, if all the sections of the spinner are the same size, then it is a fair outcome or fair experiment because all 4 of the spinner colors have the same size, and so they can all happen equally in equal chances. You can usually assume that experiments involving coins and dice are fair. An experiment consists of rolling a die. Find the theoretical probability of each outcome. So for rolling a 3, we know that one side of the die is a 3. So there's one way that that event can occur, and there are 6 likely outcomes on a die because there are 6 sides with 6 numbers. So our chances are 1 out of 6 or 0.167 or 16.7%. Rolling a number greater than 3. Well, we know that there are 3 numbers greater than 3 on a die. There's a 4, 5, and 6. So the number of ways the event can occur are 3 out of 6, which is 1/2. As a decimal is 0.5, so we have a 50% chance of rolling a number greater than a 3. When you toss a coin, there are 2 possible outcomes, heads or tails. The table below shows the theoretical probabilities and experimental results of tossing a coin 10 times. So in experimental probability, we have 3 heads and 7 tails. So if you add the number of heads and the number of tails, you get 10 out of 10, which is a total probability of 1. In a theoretical probability, you have a 50-50 shot. So you have a 1/2 chance of hitting heads and a 1 out of 2 chance of hitting tails. If you add 1/2 and 1/2, you get 2 out of 2, which again is going to be 1. The sum of the probability of heads and the probability of tails is 1, or 100%. This is because it is certain that one of the 2 outcomes will always occur. And so that is our outcome for both experimental and theoretical probability because there can be no other outcome other than heads or tails. So the probability of an event happening plus the probability of an event not happening has to be 1. The complement of an event is all the outcomes in the sample space that are not included in the event. The sum of the probabilities of an event and its complement is 1 or 100% because the event will either happen or not happen. Two events are complementary events if the sum of their probabilities equals 1, and if one event occurs, if and only if the other does not. So the probability of an event plus the probability of the complement of the event is equal to 1. The weather forecaster predicts a 20% chance to snow. What is the probability that it will not snow? So the probability that it will snow plus the probability that it will not snow will equal 100%. Well, the probability that it will snow is 20%, and if we subtract 20% from each side, we get the probability that it will not snow being 80%. A jar has a green, blue, purple, and white marbles. The probability of choosing a green marble is 0.2, the probability of choosing a blue is 0.3, and the probability of choosing a purple is 0.1. What is the probability of choosing white? Well, the probability of choosing a green, blue, purple, or white marble is 1 because those are the only colors in the bag. So one of those events has to happen. If we take our probability of green, probability of blue, and probability of purple, and put in what those values are, we can add those probabilities together, and then we can subtract it from 1 to get the probability of white being 0.4. Odds are another way to indicate the likelihood of an event. Odds express likelihood by comparing the number of ways an event can happen to the number of ways an event can fail to happen. The odds in favor of an event describe the likelihood that the event will occur. The odds against an event describe the likelihood that the event will not occur. Odds are usually written with a colon in the form of A to B, but can also be written as A to B in words or A over B. So for odds, where A represents the number of ways an event can occur and B representing the number of ways an event can fail to occur, the odds in favor of an event with equally likely outcomes is the number of ways an event can happen over the number of ways an event can fail to happen, which is indicated as A to B. Odds against an event with equally likely outcomes is the number of ways an event can fail to happen over the number of ways an event can happen, or B to A. The two numbers given as the odds will add up to the total number of possible outcomes. You can use this relationship to convert between odds and probabilities. When dealing with probability, it is helpful to know how a deck of cards is structured. A standard deck of playing cards contains 52 individual cards. So this is a listing of the 52 cards that you will encounter in a deck. We have 4 sets of 2 through 10, a jack, queen, king, and ace. So each of these is referred to as your 13 ranks. We also have 16 face cards when you count ace as a face card. So unless otherwise specified, we are going to assume ace is a face card in this case. Now you also have 4 suits. You have hearts, diamonds, clubs, and spades. The hearts and diamonds are red, making 26 red cards, and the clubs and spades are black, giving us 26 black cards. What are the odds of choosing a red card from a standard deck of playing cards? The probability of choosing a red card is the number of red cards out of the total number of cards, which is 26 over 52, which is 1 out of 2, or 50%. The probability of not choosing a red card is taking the total number that are not red, which is 100 minus your red cards, which gives us 50%. So the odds in favor are 50-50 or 1-to-1. What are the odds of choosing a spade from a standard deck of playing cards? The probability of choosing a spade is our number of spades out of our total number of cards, which is 13 out of 52 because there are 13 spades. That reduces to 0.25 or 25%. So if we want to find the probability of not choosing a spade, we take 100% and subtract it from the probability of getting a spade, which is 25%, and that gives us 75%. So the odds in favor of selecting a spade from a standard deck of playing cards is 25 to 75, or 1 to 3. Now, if you wanted to express this as odds against, the odds against getting a spade card would be the flip, 3 to 1. The odds against choosing a green marble from a bag are 5 to 3. What is the probability of choosing a green marble? The number of ways that we can pull out a green marble is 3 out of our total 8. Because remember, the 5 is the number of ways we can't choose a green marble, and 3 is the number of ways we can, giving us a total of 8 ways that we can choose something. And so that gives us 0.375 or 37.5%. So the probability of choosing a green marble is 37.5%. So far, we have explored the probability of a single event. What if we wanted to find out the probability of 2 successive events? We must first identify if the events are independent or dependent. Events are independent events if the occurrence of one event does not affect the probability of the other. Events are dependent events if the occurrence of one event does affect the probability of the other. So let's determine which of these sets indicates an independent or dependent event. And we're going to explain why. So a dime lands heads up and a nickel lands heads up. Well, the dime and the nickel both operate independently of one another, so the result of tossing a dime does not affect the result of tossing a nickel, so the events are independent. For the second example here, you choose a colored game piece in a board game, and then your sister picks another color. Your sister cannot pick the same color you picked, and there are fewer game pieces for your sister to choose from after you choose, so the events are dependent. Her color will depend on the color that you first choose, because once you choose a color, your sister cannot have that color. Suppose an experiment involves tossing 2 fair coins. The sample space of outcomes is shown by the tree diagram. Determine the theoretical probability of both coins landing heads up. So you toss the first coin, and it's going to either be heads or tails. From there, you toss the second coin, which will either be heads or tails after heads, or heads or tails after tails. So the 4 possible outcomes in the sample space are heads, heads, heads then tails, tails then heads, or then tails then tails. Only one outcome includes both coins landing heads up. So the theoretical probability of both coins landing heads up is 1 out of 4, because it is 1 out of the 4 possible outcomes. Now look back at the separate theoretical probabilities of each coin landing heads up. The theoretical probability in each case is 1 out of 2. The product of these 2 probabilities is 1 out of 4, the same probability shown by the tree diagram. To determine the probability of 2 independent events, multiply the probabilities of the 2 events. So if A and B are independent events, then the probability of A and B is the probability of A times the probability of B. An experiment consists of randomly selecting a marble from a bag, replacing it, and then selecting another marble. The bag contains 7 blue marbles and 3 yellow marbles. What is the probability of selecting a yellow marble and then a blue marble? Because the first marble is replaced after it is selected, the sample space for each selection is the same, so that makes the events independent. So the probability of choosing yellow then blue is the probability of choosing a yellow marble times the probability of choosing a blue marble. So the probability of choosing a yellow marble is 3 out of 10, and the probability of choosing a blue marble is 7 out of 10. We multiply those and get 21 out of 100. So our probability of choosing a yellow marble then a blue marble is 21 out of 100. When a person rolls 2 dice and they land showing the same number, we say a person rolled doubles. What is the probability of rolling doubles 3 times in a row? This is something that you typically see in a game of Monopoly. If you roll doubles 3 times in a row in Monopoly, you go to jail. So let's see what the probability of rolling doubles 3 times in a row is. The result of one roll does not affect any of the following rolls, so the events are independent. When you roll 2 dice, there are 36 possible outcomes, 6 of which are doubles. So here are all the possible outcomes of rolling 2 dice. And out of these 36 total possibilities, there are 6 that are doubles. So we're going to take the probability of rolling doubles once as being 6 out of 36 or 1 out of 6. Now we're going to find the probability of rolling a double, then another double. So we're going to do that by multiplying those 3 probabilities together, which is 1/6 times 1/6 times 1/6, which gives you 1 out of 216. So your probability of rolling doubles 3 times in a row and going to jail in a game of Monopoly is 1 out of 216. Suppose an experiment involves drawing marbles from a bag. Determine the theoretical probability of drawing a white marble, then drawing a second white marble without replacing the first one. So the sample space for the second draw is not the same as the sample space for the first draw. There are fewer marbles in the bag for the second draw, meaning that the events are dependent. The second draw depends on what happens in the first draw. The probability of drawing a white marble in the first draw is 3 out of 9, which is 1 out of 3 when you reduce it. The probability of drawing a white marble on the second draw is 2 out of 8 because there's one less marble in the bag. 2 out of 8 reduces to 1/4. To determine the probability of 2 dependent events, multiply the probability of the first event times the probability of the second event after the first event has occurred. So the probability of dependent events is found. If A and B are dependent events, then the probability of A and B is equal to the probability of A times the probability of B after A. So let's say there are 7 pink flowers and 5 yellow flowers in a bunch. Jane selects a flower at random, and then Lee selects a flower at random from the remaining flowers. What is the probability that Jane selects a pink flower and Lee selects a yellow flower? So on Jane's turn, the probability of selecting a pink flower is 7 out of 12 because there are 12 flowers in the bunch and 7 of them are pink. Then on Leah's turn, there is a probability of 5 out of 11 of selecting a yellow flower after the pink flower has been pulled because there are 11 flowers left, 5 of which are yellow. So the probability of a pink and a yellow is the probability of pink times the probability of yellow after pink, which is 7 out of 12 times 5 out of 11. When you multiply them together, you get 35 out of 132. In experiments with numerical outcomes, the expected value is the weighted average of the numerical outcomes of a probability experiment. To find the expected value of an event, multiply each possible outcome of the event by the likelihood or probability of that outcome, then add them together. Expected value can be used to make decisions in business, insurance settings, traffic, games, and other situations. For example, if 2 people want to end a game early, they can use the expected value to verify who was the most likely to win. You can also use expected value to determine if a game is fair when played multiple times. So in this example, you pay $5 to play a game where you draw 1 card from a standard deck of playing cards. If you pick the ace of spades, you will win $100. If you pick a face card that is a diamond, you will win $50. If you pick any other card, you lose the game. Determine the expected value, then explain whether it is a fair game and why. So an ace of spades, you have a 1 out of 52 chance because there's only one ace of spades in the deck. So you're going to multiply that by $95. Now, the reason you don't multiply it by 100 is because you have to pay $5 to play the game. So if you win, you're not winning $100, you're actually winning $95 because you're getting your $5 that you spent back. So if we multiply 1 out of 52 by $95, that gives us approximately $1.83. To get a diamond face card, there are 4 face cards out of the deck that are diamonds, because we are including aces here. 4 out of 52 times $45 gained by winning the $50 prize is $3.46. If you pick any other card than the ace of spades or a diamond face, there are 47 cards in the deck that are neither of those, and we're going to multiply that by the $5 that you lost, so -5. And that gives us a negative $4.52. If you take all of those values and add them together, that gives you an expected value of 77 cents. So this means the game is not fair because the chances of winning favor the player when played multiple times. So if you play it over and over and over again, you are likely to come out ahead. But when played only once, the chances of the player losing are greater. Thanks for checking out my video in the Foundations in Algebra series. You can subscribe to my channel. I've got the next video queued up for you, and if you need to check out any of the videos in the course, I've got the course playlist for you here as well. Thanks for watching.